All right, we've seen this many times. Chemical change can be described by a chemical reaction going from reactants to products. Here we have aluminum and bromine reacting to give aluminum bromide. We said that the arrow connecting reactants and products has the same properties as an equal sign. Therefore, there must be the same numbers of types of atoms and the same mass on both sides. We make sure of that by sticking in stoichiometric coefficients. Coefficients are numbers that go in front of the reactants and products to make sure the equation is balanced. Now we look at how to do that last time. If we were to try to balance this equation very simply, I would start by saying we have 2 bromines here, we have 3 on this side. Let's make this side even. So we'll stick in a 2, so we have 6 bromine atoms. 6 bromine atoms requires we have 3 Br2s. We also put a 2 here, so we have 2 aluminums, and that is our balanced equation. 2 aluminums, 6 bromines on both sides. This is referred to as the stoichiometry of the equation, the 2, the 3, and the 2, simply describing the molar amounts of reactants and products. This also gives what's called the theoretical yield of the reactions. Thinking about it this way, if we had 2 moles of bromine of aluminum, and we had all the bromine in the world we wanted, we'll call that excess. We have excess bromine and at least 2 aluminums, we will get 2 moles of aluminum bromide. Theoretical yield. If everything works, this is what we should get, 2 moles. Any questions? Simple stoichiometry. So let's look at a real example here. If we take ethanol, react it with oxygen, we can get CO2 and water. First thing you want to do is always check to make sure that the equation is balanced. We have 2 carbons, we have 2 carbons. We have 6 hydrogens, 6 hydrogens. We have 6, 7 oxygens, 4 plus 3, 7 oxygens. So yeah, we're balanced, we're good. Now, we are given in this problem that we have 2.5 moles of ethanol. We want to know how many moles of CO2 we're going to get. According to this equation, 1 mole of ethanol gives us 2 moles of CO2. Now, what we're trying to find in this reaction is how many moles of CO2. The number we're given is 2.5 moles of ethanol. When you do a problem like this, what you want to do is to look to see what the question and answer are, the products or reactants that are linked. CO2 and ethanol, these guys. We'll start off by making a ratio based on the stoichiometry. We are given that we have 2.5 moles of ethanol, that's right here. We know a ratio. For every 1 ethanol, we will get 2 CO2s. So that's a ratio. I set the ratio up with ethanol in the denominator because it's given. Remember, the given always goes in the denominator. And of course, we're trying to find CO2. Start off with our given. Simply multiply it by a ratio. Moles of ethanol will cancel. Do our simple math. 2.5 times 2 divided by 1, 5 moles of CO2. That's all in the world there is to a stoichiometric calculation. You look to see what you're looking for. You look to see what reactant is linked to it. And you look at the equation and just do a ratio. 1 ethanol, 2 CO2s. Set up that ratio, multiply it by the given, and you have it. Now there's another way, because you're getting more sophisticated in your chemistry. There's a simpler way to actually do these problems without writing out this full equation. And that is, instead of doing the given find, we're going to do just more ratios. A known ratio and unknown ratio. For the known ratio, it's going to be the relationship between ethanol and CO2. We start off looking at the balanced equation. What's the relationship between ethanol and CO2? Well, it's 2 to 1. Next, we look at our problem. And in the problem, we're looking to find the unknown. We'll call the unknown X, because I can. And the other known given. So up here, how many moles? That's X. We don't know what it is, it's an unknown. What are we given here? 2.5 moles of ethanol. So we have this ratio from the stoichiometry here, and now we're going to make an unknown ratio from the problem. That's simply going to be X number of moles over 2.5 moles. Now, once you get it set up, again, make sure ethanol is in the denominator on both sides. The reason this is easier is you just set up your ratios, take your calculator, and do 2.5 times 2 divided by 1. That's it. You got your answer. We'll do this the long way just to make you more comfortable. I will take this and multiply it by this side, and we get this guy. Once we're at this point, we can easily see that our moles of ethanol cancel. And again, our math is simply 2.5 times 2 divided by 1, or 5. If you think about it, this is exactly the same as given ratio, isn't it? Here's our given. We're multiplying it by the ratio. You just don't have to worry about writing it out or thinking about it. Just take the ratio directly and cross multiply. Any questions? Let's do another one then. Calcium reacts with HCl to give calcium chloride and hydrogen gas. We've done this in lab. First, check to see if the equation is balanced. 1 calcium, 1 calcium. 2 hydrogens, 2 chlorines. Yep, we're all balanced. Next, let's look at our problem. We're going to link HCl and calcium. So HCl linking to calcium. They're both reactants, but it still works. Our relationship is 1 calcium requires 2 HCl's. Now, our given here is going to be calcium, isn't it? So let's set up this ratio with calcium in the denominator. So it will be 2 HCl's for 1 calcium. Our unknown ratio, what's X? X is simply moles of HCl. And our denominator is our given. That's 3.25 moles of calcium. X over 3.25, 2 over 1. Again, on your calculator, at this point, you could just take 3.25 times 2 divided by 1 and get your answer. If you want to feel more comfortable, take this, multiply it by a ratio here. Moles of calcium will cancel, and the math is the same. 3.25 times 2, 6.5. So once you look at these things, they really start to fall into place and to be simple. Any questions? Let's look at one more here. And just for fun, as we look at this equation, it clearly isn't balanced. So why don't you take just a second and let's balance it. Now, just to prove I can, let's see. We have 2 carbons, we have 1 carbon. Let's put a 2 in here. All right. We have 6 hydrogens. We only have 2, so we need a 3 here. One of these guys ought to work. How many oxygens do we need? Well, we have 4, 5, 6, 7 oxygens. The problem is that oxygen comes in pairs, doesn't it? It's O2. So if we were to put a coefficient here, we would put in 3.5. Now, this is legally correct. They're the same numbers and types, but convention is that we want to show whole numbers only. So if you're ever balancing something and you come out with something like 3.5, just double everything. Multiply everything by 2. So instead of 3.5, we'll have 7. Instead of 2, we'll have 4. Instead of 3, we'll have a 6. And instead of 1, we'll have a 2. So the final balanced equation looks like this. Any questions? If it ever turns out like this, where you have a fraction, just multiply it by whatever it takes to make the fraction whole. All right, now let's look at the problem. Let's see, we're linking molecular oxygen and CO2. So oxygen and CO2. Our given is going to be CO2. So we want that in our denominator. Our ratio is therefore going to be 7 oxygens to 4 CO2s. 7 moles of oxygen, 4 moles of CO2. So let's set it up. There's our ratio. Now moles of CO2, moles of oxygen are the unknown. That's going to be our X. Moles of carbon dioxide, that's our number. We have a given. That's our denominator. And simply write the ratios. Now once again, the shorthand on your calculator, 1.7 times 7 divided by 4 gives you your answer. This makes it so much easier. If you multiply it out, same thing. Moles of CO2 cancel. 1.7 times 7 divided by 4. We get this as a number, but it has too many significant figures, doesn't it? This is 4 significant figures. This is 3. So let's round this to 3. 7.5 is going to round even up to 8. 2.98. All right, let's take this one step further. No, not yet. Let's do one more. Chloroacetic acid, it's called, reacts with oxygen to give carbon monoxide, water, and HCl. First thing you want to do is look and see which reactants and products you're linking, and that's oxygen and carbon monoxide. So this and this. Carbon monoxide is going to be our given, so it goes in the denominator. It'll be 1 to 4. 1 mole of O2 is 4 moles of CO. There's our ratio. Again, I put CO in the denominator because it's our given. We have an X and we have a given. X over given is our ratio. Now, all you have to do here with your calculator, don't have to multiply it out. We're comfortable with this now. 0.26 times 1 divided by 4. We get a number here off our calculator with too many significant figures. Again, we have to round to 4. This has 5, so we'll round this to 2 because that's even. Any questions? All right, this brings us to our first tutorial. First tutorial, basically these types of problems. Molar stoichiometry. A little introduction here just to show you, again, our X, our given, and our given ratio. We are trying to find the number of moles of sodium hydrogen carbonate, so that's X, and we are given 0.82 moles of sodium carbonate. Our equation, 2 sodium hydrogen carbonates give 1 sodium carbonate, CO2 and water. We're linking these two, so here to here. Our given is carbonate, so that's going to be in the denominator. So it's going to be 2 to 1 as our ratio. Everyone see that? Sodium hydrogen carbonate over carbonate. So this guy over this guy, the ratio is simply 2 to 1. Our X here, what we're trying to find, that's this, divided by the given, which is 0.82. All we do is our simple math here, 0.82 times 2 divided by 1, and we get 1.6. Even simpler than the problems that we've done previously because I tell you what the finding given are. Any questions? I'll ask you one more. Go ahead and set up the ratio here. This is for chloroethane and chlorine. Chloroethane and chlorine. Our given is chlorine, so that's going to be in our denominator. So we have 2 in our denominator. And we're looking at chloroethane, that's this guy, so that's 4. The ratio is going to be 4 over 2. You can put 2 to 1, doesn't matter. Our unknown here is going to be moles of chloroethane, that's this. Our given is 0.9922, that's our denominator. We simply multiply our given times 4 divided by 2, and we get 1984 with a decimal. Any questions? Well, these are simple stoichiometry problems based on moles. When you're in lab, you don't really think in terms of moles so much, do you? You kind of like if you're going to do this reaction, you would get so many grams of this and so many grams of that, and whatever. So what if we do a stoichiometry problem in terms of mass instead of moles? We can do that because we know that the molar mass is equal to 1 mole of stuff. So let's look at zinc sulfide reacting with oxygen to give zinc oxide and SO2. It's balanced. We're looking to see how many grams of zinc oxide, so that's this guy, from 25 grams of zinc sulfide, that's this guy. This is going to be in our denominator. Our ratio here is basically going to be 1 to 1. We will get 1 zinc oxide for every zinc sulfide. So let's write our ratio. Now, everything in this problem, the answer especially, is given in terms of mass, isn't it? So we want this in terms of mass. We can do that because we know the molar mass of zinc sulfide and zinc oxide. Just get that straight off the periodic table by adding up the formula mass. So for zinc sulfide, 1 mole is equal to 97 grams. For zinc oxide, 1 mole is 81 grams. So instead of writing a mole ratio like that, we can just write it this way. 97 grams is the same as 1 mole, and 1 mole of zinc oxide is the same as 81 grams. So we just convert them to mass. Now, when we look at our problem, our X is going to be grams of zinc oxide. our given is going to be grams of zinc sulfide. So we can just write our ratio. That's X, and that's the given. Now, you know, I hate it when this happens. Sometimes, even I, forget to notice which one is truly given and which one is what you're trying to find, and you put your ratio in upside down. Okay? That's the bother. I mean, they match, sulfide on the top, oxide on the bottom, but at this point we suddenly say, oh my goodness, I should have reversed them, shouldn't I? What do? Just flip them both over. That's all. As long as oxide's on top, zinc's on the bottom, you're good. If you do it wrong, just flip it over. Makes the math so much more apparent. 25 times 81 divided by 97. And we get about 20.9 grams of zinc oxide. So this is simple stoichiometry, except expressed as mass. Any questions? Now this ratio here, which is expressed in terms of mass, is called a mass ratio. Not surprising, kind of makes sense. The only time you need to think when you do a mass ratio is if the stoichiometry here isn't even. So let's look at another one here. We have water and HF. Water and HF. Again, we're looking at mass, so we have 62 grams of HF as our given. We're going to start off this problem exactly the same way, and that is to look at our molar ratio. HF should be our denominator, that's our given. Takes 2 moles of water, 4 moles of HF. So let's write a ratio, 2 to 4. You can write 1 to 2, doesn't matter. Now, we are given the molar masses here, aren't we? There are 2 waters and they're 18 each. So to get the mass ratio, we want to multiply this by 18. Likewise, we have a 4 HF. Each one weighs 20. We need to multiply that by 4. 2 times 18, 4 times 20. This is the stoichiometry from the equation, and this is the molar mass. If we multiply this out, we get a ratio 36 over 80. That's our final mass ratio. A simple way to think about a mass ratio. Simple way. If we have 36 grams of water, we will get 80 grams of HF. Simple way to think of it. 30 grams of water, 80 grams of HF. All right, what do we do if we have a ratio? Well, we're going to multiply it by our given. This is X, that's our numerator. Here is our given, that's our denominator. X grams of water, 62 grams of HF. On your calculator, 62 times 36 divided by 80. And and we have 28.1. Saves you from having to go back and forth in terms of moles and mass. You can do the whole thing in terms of mass if you simply stick in a mass ratio. One more time. Intuitively, this simply says 36 grams of water gives you 80 grams of HF. Intuitive. And that brings us up to the second tutorial here. What would we call this stuff? And not Ku. Cobalt is a transition metal, so we have to show the charge, don't we? Oxygen is always -2, so this is cobalt 2 oxide. Oxygen is still -2, we have 6, so each of these must be 3, cobalt 3 oxide. So, question here. How many grams of cobalt 2 will we get from 41 grams of cobalt 3? What's your ratio here? 40 grams of cobalt 3, this is our given. Cobalt 2 is our unknown. So it's going to be 4 to 2 is our molar ratio. To make that into a mass ratio, we'll multiply the 4 times 79, multiply the 2 by 165. We'll take our mole ratio, convert it to a mass ratio with our given in the denominator. So our mole ratio, 4 cobalt 2s give 2 cobalt 3s. Every cobalt 2 weighs 74. Every cobalt 3 weighs 166. If we simply multiply this out, we would get our mass ratio. Algebraically, you really don't have to multiply it out. You can simply take this ratio as it is, multiply it by our given. The math is a little more cumbersome, but it's a nice shortcut. 41 times 4 times 75 divided by 2 divided by 166. Do all that math on your calculator in one series of strokes. Everything bad cancels, and you get 37 grams of cobalt 2. Any questions? All right. As we have done this problem here, we have cobalt 2 reacting with oxygen to give cobalt 3. The assumption here is that there's enough oxygen there so that the reaction goes to completion. Oxygen, just like we saw with bromine, first set of slides, is in excess. The amount of product you get is going to be limited by the amount of cobalt 2, number of grams. This whole concept is called limiting reactants. Now, you can do limiting reactant problems that are extremely complicated. We won't. That's for general chemistry. But we want to be introduced to the concept of a limiting reactant versus an excess reactant. Limiting reactant will tell us how much stuff we can possibly get. The thing that we have too much of is our excess reactant. Now this is, I think, easiest understood if you think about gloves. All right, it's starting to warm up. We don't need gloves anymore. But as wintertime approaches, generally you look in your closet on the floor and you see a pile of kid gloves. And you got to come up with pairs to get the kids, right? So in this pile, we have 4 left-handed and 3 right-handed. Therefore, if we want to make pairs, we reach in our stack, we can make 1. We have another pair, that's 2, and we can take that and make 3. We have 1 left-handed glove left over. The left-handed gloves are in excess because when the reaction's over, they're still sitting here. Right-handed gloves limit how many pairs you can make. The limiting reactant and the excess reactant. Now, instead of calculating this out, basically the way you do these things is you take each of your reactants, do a stoichiometry, see how much product each one makes, and that will tell you which is limiting and which is not. It's not complicated, but it's tedious. It's just lots of calculations. So again, we're not going to do limiting reactant problems, but intuitively, I want you to be able to understand it. So we're going to do a cartoon. Now, this reaction right here and the cartoon have appeared on virtually every exam for the last 3 years. So, remember that. Look at the cartoon. In this reaction, we are taking 3 moles of fluorine, reacting with chlorine to make 2 moles of chlorine trifluoride. First thing you want to note is that every 2 atoms of chlorine, that's Cl2, require 6 atoms of fluorine, that's F2. So that's our stoichiometry. So from this cartoon, you can see if we took 1 Cl2, we would need 3 fluorines to go with it, and we would make 2 chlorine trifluorides. We can do this again. Take another chlorine, take 3 more fluorines, and make 2 more ClF3s. When we're done with this, we're left with chlorine by itself, aren't we? And 4 moles of product. The question here is which reactant is limiting? Limiting was our fluorine. We've used it all up. Excess reactant is the chlorine. We have some left over. So just make sure you understand the concept. Whatever's left over is called excess. Whatever is totally used up is called limiting. I can assure you on exam 2, you will see this equation with some sort of a thingy. So make sure you understand this concept. All right, so As I said early in the lecture here, when you have a balanced chemical equation with the same numbers and types on both sides, this number here, this 2, gives us the theoretical yield of the reaction. If we have 2 moles of aluminum, excess bromine, so it's left over, we will get 2 moles of our product. That is our theoretical yield. Excess aluminum will form 2 moles of aluminum bromide. It's our mole ratio. Again, this is our theoretical yield. Any questions? When we speak of yield, there are 3 things that we talk about. The yield is how much stuff you get. Okay, that's simple. The theoretical yield is what we calculate based on the stoichiometry. In the previous slide, that was 2 moles of product. The actual yield is what you get when it's all over. So you do your reaction, you scrape up all your product, you weigh it, and see how many moles you got. That's the actual yield. Now, why isn't that exactly 2? Very seldom it's ever going to be equal to theoretical yield. When substances react, they follow what's called an energy profile. And typically there is one major pathway that's the lowest energy, and that goes and gives you your product. But there are other pathways that can follow as well that will give other products. That reduces the actual yield of the product. Also, if you do the experiment in the lab, and you're scraping stuff out of a tube or something, you're going to leave some behind. If you have a lab partner that sneezes in the middle of it and blows it all over the floor, you're going to lose some, scrape it up off the floor. So actual yield is always less than theoretical. Percentage yield is simply the relationship between actual and theoretical. To get a percent, you would take actual, divide by theoretical, and then multiply by 100. That's how you get percent. All right, let's see this. This is popcorn. If you count quickly, we have 20 kernels. The theoretical yield for popping would be 20. 20 popped kernels, right? Pop it in the pot. Let them pop. Come on. Dump it out. And we get 16 that popped and 4 that did not. So our theoretical yield is still 20. The actual yield is 16. How do we get percent yield? 16 divided by 20 times 100. And that's 80%. Actual is what you get, theoretical is what you should. The ratio, actual over theoretical times 100 gives you percent. Simple problem here. We're doing this reaction. We have 5 moles of sulfur. According to the stoichiometry, we should get 1.7 moles of aluminum sulfide. When we're done, we scrape it all together and we weigh it. We see we get 1.5 moles of aluminum sulfide, not 1.7. Calculate the percent yield. The theoretical is 1.7. The actual is 1.5. Take that ratio. Theoretical is always on the bottom. We're going to take this ratio, multiply by 100, do our simple math, and we get 88%. Let's do one more. Nitrogen monoxide reacts with oxygen to give nitrogen dioxide. Nitrogen monoxide is a very, very reactive compound. And it can easily grab an oxygen from O2 to give NO2. All right, we take 10 grams of NO. We have 9.7 grams of, we get 9.7 grams of NO2. Oxygen is in excess. What's our percent yield? I think the simplest way to do this is to simply convert these into moles and take our ratio. So, for our NO, our molar mass is 30. We got 10 grams, and this is 30. For NO2, we got 9.7 grams yield, and its molar mass is about 46. So what do we remember? Mass over molar mass gives us moles, doesn't it? I told you that was important. Mass over molar mass gives us moles. Mass over molar mass, we started with 0.33 moles of NO. For NO2, mass over molar mass, we got 0.21 moles of NO2. To get our percent yield, we would simply take actual over theoretical times 100 there's a ratio times 100, 63%. Any questions? All right, there is a tutorial that goes with this one, percentage yield. Unfortunately, when I wrote this particular tutorial, I was teaching general chemistry, and it is a little cumbersome for intro chemistry. So it's not one that you do for credit, but let's just take a look at it. Here we have 15.6 grams of trifluoroethane, and we get 6.6 grams of CO. What's the percent yield? What we're going to have to do here is make a mass ratio. Mass ratio, given compound in the denominator, and we're going to calculate the theoretical yield of CO. Now, we are given molar masses. This is our mass ratio, 2 COs for every 1 trifluoroethane. Multiply this by its molar mass. Another way to say this, 56 grams of CO from 84 grams of trifluoroethane. That's what the mass ratio tells you. We would take that, multiply it by our given, and we would get grams of CO. That's our theoretical yield. So, theoretical yield is 10.4. The actual yield in the problem was 6.63. Percent yield is simply this ratio times 100, multiply it out, times 100, 64%. Now, like I said, this one really isn't for credit. So, but if you want to do it online on Chemistry Online. And after you get 5 correct, hit submit. Make sure you put in your email address. Don't change mine. Leave it as intro.com, whatever. Don't change that one. Just put in yours. And if I see that come up, I'll give you the 5 points credit. Okay? But it's not officially a Blackboard one because I think they're a little bit too sophisticated.